So the last reaction we're going to learn in chapter 22 is how to take a nitrile and make a ketone from it. So if we look at the starting material, and let's just number the carbons. So we have 1, 2, 3 carbons here, and then an R group, we'll just leave that as R. But in the product, we have 1, 2, 3. So somehow we added this number 4, this fourth carbon of the CH3 there. This is a new carbon. This is a new addition. So somehow we are going to learn a way to add a CH3 to carbon 1 here. And what you guys should be thinking about is, oh, it's a carbon, and this position, is this position electrophilic or nucleophilic? So pause it, think about that. Is it electrophilic or nucleophile? And unpause, and here's the answer. It's electrophilic, right? Well, nucleophiles have been adding to that position, negatively charged things. So what negatively charged carbon nucleophiles do we know about? One thing that we learned about is alkynes. We can deprotonate an alkyne and make that a nucleophile. The other carbon nucleophiles that we know about have all been organometallics. And that's what we're going to use. So it turns out that organometallics, and we saw this a lot last unit, organometallic nucleophiles have, I guess we could say have or had similar reactivity to lithium aluminum hydride, and we'll also say dival H here. And it turns out in the last chapter they looked a little bit more like lithium aluminum hydride. Here they're going to look a little bit more like dival H. So what are organometallic reagents? Which ones have we learned about? And the ones we've learned about are grignards and organolithiates are the most common carbon nucleophiles that we've used recently. So what are grignards and organolithiates? They are a carbon, so CH3, and then an MgBr. This is a covalent bond, but it also kind of acts like an ionic bond, so we often would write that in class as CH3 minus with MgBr plus. And just like the other nucleophiles that we learned about, they're going to add to the most electrophilic position on the nitrile. So this CH3 minus is going to be attracted to the partial positive that's on this carbon. So we can draw the electrons of that CH3 adding to that position, and the electrons going from that pi bond up to that nitrogen. So if we follow those arrows, the intermediate structure that we're going to have here is this imine. And imines, this is a Grignard reagent. We have to use aprotic solvents with Grignard, so we're in something like diethyl ether. This imine, in aqueous conditions, would hydrolyze to the ketone, but it can't do that under these conditions because there's no water around. Also, we can have this N minus. That N minus has an Mg, we'll say MgBr plus counter ion that's close by, so we can say, oh, this is the species that is produced when we add our first reagent. So this is produced. This nitrogen doesn't have like a full bond to anything. It's just has a counter ion of this MgBr, and this is a pretty stable system. So we went downhill as far as energy in this one step because we started with CH4. If you think about the stability of CH4, we would relate that to the conjugate acid, which is CH3. We'd relate that to the conjugate acid CH4, which has a pKa of 50. So it is not acidic at all, which means that this is a very strong nucleophile. So if we compare that to an N minus, the conjugate acid that would be related to is NH3. That has a pKa of 38. So essentially we're forming the more stable anion. This is a more stable anion than CH3 minus. So we went downhill in this first reaction. So how do we change out an imine, and it's a negatively charged imine, for a ketone? And to do that, all we have to do is add water. So that's the second step here, is adding water. The water is just going to, first this nitrogen is going to protonate, then water will be able to add in there as a nucleophile, and then we're just going to get the imine hydrolyzed to form the ketone. So this is just going to be an equilibrium. There's going to be a lot of water around. That's going to add in there. It's going to kick out NH3. And ultimately, this is going to be the products of that reaction. Usually we omit the inorganic products, so we only write the things that have carbon on them, so that's why we often don't write out that other thing that's formed. So this is a way, we know how to make grignards. We know grignards they can be pretty diverse. We could have this type of grignard, or organolithiated. We could have this type of grignard. All of these different R groups can be added to this position by addition to nitriles. So it's a pretty powerful transformation. So lastly, we'll fill in our blanks on the page 17. So blank and blank, add to nitriles, producing ketones with the R group attached. So what do I mean by R group? I mean, as far as R MGBr or R lithiate, that R is what is being attached right here. So in this case, the R would be the CH3. So we'll write grignards and organolithiates add to nitriles, producing ketones with the R group attached. So whatever that R group is adds into that position, and then that becomes a ketone once that imine is hydrolyzed. So pretty powerful transformation. So now we know how to make nitriles by a standard SN2 reaction. We know how to reduce nitriles. We know how to add carbon nucleophiles to nitriles. And we also know how to hydrolyze a nitrile to a carboxylic acid. And once we're at the carboxylic acid, we can get to any of the other carboxylic acid derivatives. So really, at this point in the chapter, we can do anything. You can do anything. You can do anything you want. All right, go do it.